My name is Ben Hovey, and this is my Physics Lab 1, which is about constant velocity. The purpose of this lab is to observe the motion of an object, in this case it's a roll of tape, traveling at a constant velocity without changing direction. Then I will compare that motion observed in reality to the predicted motion calculated using a computational model. Some assumptions we will be making is that there is no resistance of any kind, therefore there is no friction or air resistance. That the normal force equals the gravitational force, or in other words, that we're on a completely flat surface, which won't allow any acceleration or deceleration, and that the object travels in a straight line. The displacement is only observed on the x-axis, and therefore the y-axis and z-axis are not represented. So fundamental principles, we got Newton's first law, an object won't move or change direction unless acted upon by a force. And Newton's second law, the momentum principle, which is the most fundamental principle of this lab, which relates to net interactions between the systems and their surroundings to the observed motion of the system. In other words, the net force is equal to the change in momentum or the change in time. Two very important formulas we'll be using are the position update formula, shown right here, and the velocity update formula, shown here. Now that velocity update formula was derived using Newton's second law. So as you can see, if you mess around with Newton's second law, you can come to the conclusion that V final equals V initial plus F net divided by M times delta T. Now, of course, we are assuming that there is no net force, as we said earlier, with no resistance, and that the normal force equals the gravitational force. And with this whole thing becoming zero, we can then assume that the final velocity is equal to the initial velocity. The experiment, of course, is to observe constant velocity as an object, in this case a roll of tape, moves. The system is the roll of tape, the surroundings are the applied force, gravity, which of course we are forgetting, and friction, which is also negligible for this experiment. The initial conditions are as such: 0 meters for position and 0 seconds for time. So after recording a video, I went and put it into Tracker, as you can see here, and I then recorded the point or the center of mass to the best of my abilities over this time interval, as it passed through 1 foot, or about 0.3 meters. Let's not do that. Okay. So now I used those numbers that I collected right here to find the average velocity, which is equal to the change in position over the change in time. As you can see here, my final position was about 0.3 meters, and my initial position was about 0.0137 meters. Divided that over the total change in time, which is 1.5 seconds, that gives me 0.191 meters per second. Okay, after getting those numbers, I plugged them into my computational model using GlowScript. As you can see here, the initial velocity, which is also equal to the final velocity, is 0.191 meters per second. Of course, the roll of tape's mass does not matter since the F net equals 0, and as you can see here is my velocity update formula, which of course the F net equals 0, meaning that this will just be final velocity equals initial velocity, and then my position update formula. After plugging those numbers into GlowScript, I was able to get this position versus time graph, which is very linear, as you can tell. When I plot that against my observed, or when I plot the observed versus predicted, and I compare the two, you can obviously see that the predicted is very straight and linear, whereas my observed is slightly crooked and also greater than the predicted motion. And this is probably due to the fact that my surface was not completely level. Some possible errors. So outside forces are definitely an error, and the reason why my motion observed in reality is different than the computational model, as seen in these two graphs. The gravity is most likely the case that changed this too, and that's because this surface is most likely not level, and it actually caused the object to accelerate as it moved to the right. We can also assume that there's a friction and air resistance involved in this. All the errors could be the tracking errors, as when I was plugging in the center of mass on the tracker, I most likely made errors in the exact center of mass as it was moving along the screen. And then videography errors, as I assumed my camera was probably not perfectly perpendicular to the surface I was recording on, and I definitely rolled the tape at an angle that was not perfectly straight. So now some what ifs. What if the x-axis, the plus x-axis, and the negative x-axis were interchanged? Well, nothing would change in the numbers or the data collected. In fact, the only thing that would change would be the slope of the graph would be negative. As I said, the data collected would still coincide with the previous data presented. What does it all mean? can you determine the net force, or the number of pushes and pulls acting upon this object, in this case a roll of tape, to be 0? Well, in a computational model, yes, we can set the net force equal to 0, but in reality, we cannot. With gravity, friction, air resistance, and many other gravitational forces acting on this roll of tape, there is no true way to obtain a constant velocity, as there will always be some force acting upon this object.